So we've been talking about, the name of the lesson that we started on Friday, properties of solids. And what we want to do essentially is we want to take our knowledge of intermolecular forces, which ultimately comes from our knowledge of, the shapes of the molecules, the polar bonds, and therefore eventually polar molecules, again, of the molecules, taking all those properties that we've learned about atoms and molecules and applying it to two substances so that we can critically evaluate the way those substances should behave when we encounter them in the laboratory or in the real world. Just to quickly review the substances that we looked at on Friday, we looked at what came before, ionic solids, right? We looked at ionic compounds. Very straightforward. We've seen ionic compounds in the past. Repeating ionic units. The bond structure is very directional. Again, we've been using the term localized and delocalized to describe the electrons. In an ionic substance, the electrons are localized because they're locked into the ions. So because they're very directional, we have a very strong lattice structure. That means that we've got high melting points. Ionic compounds are brittle. They're very hard, all right? They don't conduct electricity in solids because their electrons are localized in the ions. But if you melt them or dissolve them, that sets the ions free, and therefore they will conduct electricity in the aqueous state or in the liquid state if we melt them. And it's not because we've set the electrons free, but it's because we've set the ions free, and those ions can move, which is also a movement of charge, which counts as electrical conductivity. We then talked about metallic crystals. That was an introduction to you. I could move back one slide here and talk about, and just to kind of illustrate that, right? Remember, metallic crystals we consider to be made up of a bunch of cations of the metals with their valence electrons able to freely move from one cation to the other. They're allowed to freely move because we consider the valence orbital to overlap with adjacent valence orbitals, which then creates one great big delocalized orbital for those valence electrons to move from one nuclei to the other nuclei. That means that we have very delocalized electrons, and therefore the metals can conduct in the solid state because those electrons are able to move freely. The bonds themselves are non-directional because we have the electrons being attracted to multiple centers at the same time. They're being attracted in all kinds of different directions. And so due to the fact that that bond is non-directional, we can have malleability and ductility. If we apply a force to a metal, we can cause that metal to deform without the overall structure breaking apart. So metals are not brittle. They're malleable. You can bend them, all right? And again, that's because of this delocalized, non-directional bond from those valence electrons, okay? All right, so there's a little summary of what we've seen so far. Now let's talk about, and I'm going to jump ahead here, we've seen this. Now let's talk about small molecule crystals. And the reason I'm talking about them being small molecular crystals, the last kind of classification of matter that we're going to be dealing with deals with something called a network molecular crystal, and they're very different, so we're going to be differentiating between them. And you've probably never heard of or had a description of a network molecular crystal. Once we see this in a moment, you'll understand. So when we're talking about molecular crystals, especially small molecule molecular crystals, we're describing essentially what it looks like when something like water freezes, all right? So we're talking about good old regular molecules that you know. We're talking about all those molecules we drew when we were drawing 3D Lewis diagrams, right? They could be polar molecules. They could be non-polar molecules. So when we talk about small molecular crystals, we have a very wide range of stuff that we're really talking about. When you're talking about ionic compounds, it's pretty cut and dry. Cation, anion, repeat the units, make a lattice structure, you've got a salt crystal. When we're talking about metals, also very cut and dry, all right? Metals, you know, bunch of, I don't have the picture up anymore, but, you know, delocalized electrons, they can travel freely wherever you want, you bend them. Metals behave as metals. But when we're talking about small molecules, molecular crystals, we could be talking about highly polar substances like water. So water freezes 0 degrees Celsius. We have ice. It's a very ordered crystal. But we could be talking about nonpolar molecules, iodine, I2. We could even be talking about H2, which really cannot be solidified because there are so weak of London forces between those two that we've got this great range of possible melting points and boiling points. So this is probably the most diverse group of them all. So it's kind of tough to put a generalization on them, but we'll give it our best shot. So we can have elemental molecules, iodine, sulfur, you know, any of the Hofbrinkel ones, you know, nitrogen gas, oxygen gas, fluorine, et cetera, et cetera. And we could be talking then about compound molecules like water or carbon dioxide. Again, very different properties. So let's try to classify their properties, but again, they're very diverse and they really depend on their polarity to determine how they're going to behave. They tend to have relatively low melting points and boiling points. When we say relatively, we're talking relative to ionic and metallic, right? Ionic compounds, high melting points. Metallic compounds, also very high melting points. Ionic has high melting points because you've got complete full charges holding those ionic compounds together with the directional bonds. And metallic has high melting points because that delocalized bond is able to absorb the vibrations of the heat without it blowing the crystal apart, and so it can absorb a lot of heat energy as well. When you melt a small molecule ionic crystal, you're breaking, you know, some London forces, not very strong. Let's say you had solid carbon dioxide. It's called dry ice. You guys probably knew that. And it melts at around negative, I think, 70 or 80 degrees Celsius. It doesn't actually melt, it sublimes, it goes right into the gas state. It doesn't matter. But what holds those carbon dioxide, you know, molecules in a solid? London forces do. So it's not going to take much to melt those. All you got to do is pull apart some London forces, put a little bit of heat in it, and it goes. If you have more polar molecules, then it's going to take a little more energy to break it apart. That's what's happening in water. So again, relatively low relative to ionic and metallic. They're not very hard. Ice can be pretty hard. That's a pretty good, robust crystal. But that's being held together again by hydrogen bonding. So that's pretty strong. Paraffin wax from just a candle, held together by London forces of very long chains of carbon molecules. It's a hydrocarbon, it obviously combusts. And wax obviously is not a very hard crystal. You can easily deform wax between your thumb and your finger, and so they are easily deformed, all right? And that's because the forces holding them together are not as strong. Non-conductors of electricity in the solid and liquid state, and when in solution, the molecules maintain their integrity, they hold together, we don't have charges getting away. And again, it's because the electrons are all localized in their bonds. The electrons are locked in the covalent bonds, and so they're not free to move, so they cannot conduct. Even when you dissolve them or melt them, the electrons are still locked into the bonds, and there's no overall ionic charge, so there's no ions to separate away. Okay. Properties of small molecule molecular crystals can be explained by the intermolecular forces that hold them together. So if you're comparing melting points, and that's what we've come down to at the end of this unit, you know, which one melts higher, which one melts lower, we've got to go back to our lessons on intermolecular forces. So if I'm having you classify or you know, rank melting points or boiling points, if you get a couple of molecules, you got to go back to your lesson on intermolecular forces. You're counting electrons. You're calculating delta ENs. You're, you know, looking to see if there's hydrogen bonding in there, and then you're giving them the appropriate rank. So we essentially have covered this. We covered this in the lesson previous to this lesson. I guess I'm including Friday and today as one lesson because it really does kind of go hand in hand. Now, the other day I gave you a sheet. It's not the greatest because it didn't come out as dark as I wanted it to, but I slapped it together like 2 minutes before class. That had various images illustrating various representations of solids for these. And my next slide has that picture on there, and that's representing an ice crystal. It's not the best picture in the world. Let me take a look at what that looks like for a second. Oh yeah, that was a horrendous one. I got to make it larger, a little darker. So here we've got a representation of an ice crystal. Now, I've been trying to think of what I want you to write down underneath some of these things. And that's, again, it's because I'm kind of changing the way I'm presenting it. And in the last ones, I kind of wrote down whether we've got localized or delocalized electrons and whether our bonds are directional or non-directional. Localized and delocalized electrons will give you the electrical conductivity, right? Localized electrons can't conduct electricity because they can't move around, and delocalized electrons can conduct electricity. In this case, we're looking at ice, and so if we were looking at the electrons, oh, that's turned back to green. Why isn't it yellow anymore? It's kind of bizarre. How would you describe the electrons in these molecules? Are they able to move freely any great distance, or are they locked in position? Yeah, they're locked in position. These are localized. They're localized within the covalent bonds. Localized electrons. They're locked in covalent bonds. And I'm not going to make the conclusion from that, but if you memorize that, then you can think, all right, non-conductivity. They're not going to conduct. Those electrons are not able to move freely. I guess if we're going to use that as a memorizing technique, you got to be careful with the ionic, because ionic are locked in as well. They're locked into the ions, but because they're ions and those charges can move, that is electrical conductivity. Now, this particular example, I'm going to put here for ice. How would you describe the bonds between adjacent water molecules in this crystal representation of ice? Would you describe them as being directional or non-directional? What's that? Yeah, these are very directional bonds. When water freezes, the water molecules orient themselves in a very specific manner. They actually form some kind of hexagonal structure. Each molecule, one is perpendicular to the next. That's allowing 4 hydrogen bonds for each one. For ice, they're very directional bonds, very much like an ionic solid. And I think we already know this. Like an ionic solid, ice is brittle, right? You put a force on it, it'll crack, it'll fracture. And again, that's because of the directional nature of the bonds. Depending on the type of molecule, it can be less organized. Like if you had very large molecules, like I said, like paraffin wax, or even in something like tar, you don't get this directionality because the molecules are large and are able to kind of bend and change shape and rotate around that. They're not like a stick. They're more like a piece of string. So when certain molecules get up against other ones, their orientation might be different. It could be a chaotic orientation, so you don't have this nice directionality, and that's what makes wax kind of soft. And same with tar, it's kind of soft, because those big molecules can't get themselves lined up, and you have very non-directional attraction between those. But for ice, very directional. Okay. You could take any molecule and analyze it, like that, but obviously there's a lot of molecules, and we can't obviously cover everything. Water is a good place to start. So now on to the last one. A covalent network crystal. Textbook might call it a covalent network solid. Textbook also, I think I was flipping through it, and I think it calls it a molecular network solid. Covalent and molecular are interchangeable. I think you guys are getting the idea of that after enough chemistry here. Covalent network crystals are completely different than our small molecule molecular crystals, and there's really no way to kind of describe it until I give you some examples. So I'm just going to have you write it down. Composed of atoms which are joined by strong directional covalent bonds in a three-dimensional arrangement of atoms called a covalent network. Picture probably better to explain this than for me to just kind of talk it through. Examples of covalent network crystals include diamond, graphite, silicon carbide, and quartz, silicon dioxide. When it comes to me testing you, once you understand what these things are, those will be the examples that I will have on tests. So I need you to memorize that these are your examples of covalent network crystals. Because like if you don't know it's a covalent network crystal without me telling you, I'm not going to throw something at you that you wouldn't, have seen. So if I ask you to maybe describe the bonding in silicon dioxide, I need you to recognize that that's my example of a covalent network crystal and then describe it as such, right? So in other words, those are our official, ones that I can use on tests, et cetera, et cetera. Okay, let's just go and start looking at some examples of this, and then I'll be able to explain it a little clearer. So actually, I'm going to jump ahead, and I'm going to first talk about diamond, all right? So I'm going to go to the diamond example. Carbon is a very special atom, all right? We're going to be, our last unit is going to be on organic chemistry, which deals with all of the exciting different ways in which just carbon can bond, all right? Carbon is obviously a very important atom for life. It's the basis of most of our biological molecules. And the reason that carbon is very important and bonds in such special ways has things to do with its size. It's fairly small, which means its 4 covalent bonds can spread out very nicely, and the fact that it can form 4 covalent bonds with essentially itself. And diamond is kind of the best representation of this ability to create these bonds with itself. In a diamond, every carbon is sp3 hybridized with an adjacent carbon. So it makes 4 sp3 hybridized bonds, 109.5 degrees, with an adjacent carbon. The atoms that we looked at and the molecules that we looked at had carbon sp3 hybridized to something like hydrogen. And if that's the case, then the molecule comes to an end. It's not a very exciting molecule because we've got terminal atoms on each of those bonds. But if you take carbon and you sp3 hybridize it with another carbon, then that carbon is able to also form 4 sp3 hybridized bonds with more adjacent carbons. And in a diamond, you have one giant molecule. It's a continuous step structure of covalent bonds going from one carbon atom to another carbon atom to another carbon atom. So essentially, a covalent network solid, like diamond, is one giant molecule. One molecule with billions and billions and billions and billions of atoms that are all covalently bonded to each other, all right? For diamond, and I'm going to put some notes down here, right? Each carbon is sp3 hybridized and bonded to an adjacent, I'm in trouble on adjacent on a Monday morning, adjacent carbons. It is one very large molecule. All right? Now, in an ionic solid, we have attraction of ions holding them together, fairly strong. In a metallic compound, we have those delocalized electrons trying to hold everything together, fairly strong. But in a covalent network solid, we have very localized, very strong covalent bonds holding the adjacent atoms together. So this is a very, very strong structure. Covalent bonds hold the crystal together. In a chemical change, when we do chemistry, we break covalent bonds and we form covalent bonds. Those are chemical reactions. When we melt something, that's a physical change. When you melt something, you break intermolecular forces. Ions come apart. Maybe water molecules break their hydrogen bonding and away they go. You technically cannot melt a diamond. You technically cannot melt a covalent network solid. Because if you try to melt it and you try to cause all of those particles, say the carbon atoms, to move freely on their own, what you're doing is you're essentially breaking covalent bonds. That's a chemical change. When you break covalent bonds, you're changing the substance chemically. So if you were to attempt to melt a diamond, you wouldn't get a diamond back when you were done, because you've broken all of those sp3 hybridized bonds and you've sent the carbons on their way. Essentially, you get a diamond hot enough, you may break those bonds, but if it's done in the presence of oxygen, oxygen is going to rush in and bond with those carbons. You're going to make a whole bunch of carbon dioxide and your diamond is gone. What have you done? You've essentially burnt your diamond. You can burn a diamond. You just need to get it hot enough. It would be the equivalent of its melting, but you'll never get it back. Well, you'd have to put it under vast amounts of pressure, maybe deep in the earth where diamonds are formed because of heat and pressure, but it wouldn't be very cost effective to get your diamond back. So we don't want to try to melt them, because when you try to break the bonds holding a covalent network crystal together, you're literally doing a chemical change. So you're not going to get it back. It's a chemical change. So super, super strong, held together by covalent bonds, and super directional. The tetrahedron is the strongest shape three-dimensionally that you can create, because it's always being supported on that diagonal. There's always strong support. So to summarize and to get an idea of the properties here, directional bonds sp3 tetrahedral directional bonds, very directional bonds. How about the electrons? The electrons are, they're very localized. They're locked into those bonds. Electrons are localized. So I've been trying to get you to focus on those two things. It means a diamond is super strong, very difficult to shatter it. You could do it, but very difficult to, and it's a non-conductor. Your electrons are not going to be able to move from one end to the other, okay? The diamond is one of the strongest structures in nature because of that sp3 hybridization, and because it's being held together by covalent bonds, all right? Okay, excellent. Let's move back up to this one here, which I think on your sheet it says graphite, right? Another form of carbon, all right? And actually, the study of carbon and the way it behaves structurally, not necessarily biologically, but structurally, is a very exciting and interesting aspect to get into if you're getting into chemistry right now. Like, it's kind of a neat thing. I started to work on stuff like this in my fourth year, and I think if I'd continued on maybe and got a master's or even a PhD, I would have been working in surface sciences, and I'll explain why in a moment. Let's talk a little bit about graphite. Graphite is actually the more stable version in which we find as chemists most of the carbon on Earth, right? If we find a hunk of carbon, it's typically in the form of graphite. Coal, there's a lot of coal as well, and coal is kind of like super disorganized carbon. It's carbon that hasn't got itself organized in a nice kind of fashion. It's got carbon molecules that are kind of bonded to whatever's nearby, and it might be some carbon molecules, but they're not organized nicely in these structures. In terms of graphite, each one of these carbons are bonded to 3 other sp2 hybridized carbons. Each carbon bonded to 3 sp2 hybridized carbons. That means that each one of these rings has 3 double bonds alternating. And the next ring beside it also has 3 double bonds alternating. What that means is, and each one of these double bonds can have a resonance structure where the adjacent double bonds are in place, just like benzene. Remember we talked about benzene? It was on the video. Benzene has 2 resonance structures. That's that ring structure, alternating double bonds, and then the other alternating double bonds. Graphite is like taking benzene rings and connecting them side by side. So this is an infinite array of benzene rings. What that means is each of these carbons has p orbitals sticking up and down above and below the ring. All right? You could do that for one ring. It wouldn't hurt. Can you see it? You see how I kind of got the little p orbitals going up and down? They're probably larger than that, but that's okay. In this representation, they would be larger. And because this is a resonance structure, it means that the electrons that exist in those p orbitals are able to move freely from one pair to the next. And I'll try to do the bottom as well. I'll just do the bottom couple of rungs, and that's it. It goes in behind. I don't know if can you see it? So we've got this pi structure that extends from one end of the molecule to the other end of the molecule. There is a delocalized pi structure that extends across the, I don't even know how to describe it. The molecule, it extends from one end of the crystal to the other. The crystal that extends across the crystal. This gives graphite special properties. Most covalent network solids have their electrons locked into covalent bonds. And these sigma bonds, those electrons are locked in. But because there's this delocalized pi structure that runs all the way across the top and the bottom of a layer, then this substance conducts electricity. Graphite is a very special case. I'll put right here a little therefore. Therefore, it conducts. Other properties that come with this pi structure. There is a very weak attraction of the pi structure of one layer with the pi structure of the adjacent layer. So I'm going to put right in here, very weak attraction. It's almost like London forces attraction. All right? So graphite's a weird crystal in that within one layer, there are strong directional bonds, but with adjacent layers, there's a weak London forces attraction. So it's a combination of strength within one layer, and weakness with adjacent layers. Those of you who are writing with pencils right now are using this property of graphite, right? We use graphite in our pencils because as you drag the pencil along the surface of the paper, layers of graphite are sliding away from each other. And what you're doing is you're laying down layers of graphite. And it's because of this weak attraction between adjacent layers that allows layers to come off at the end of that pencil. And you're laying down layers of graphite. I've often tried this. Every time I think about it, I think this should work, but it fails me. I take a pencil and I make a really thick, dark line, and then I take a conductivity meter and I touch it across that line, hoping that I'm able to get electrical conductivity. It never works, and the reason is each little piece of graphite that comes off of that little tip, they're not connected. They're not being bonded together, right? They're individual little layers. So each little piece that comes off the end of the pencil will conduct. If I could get to that little, that fine tip that you're laying layers down, it would conduct. But by laying them down on top of each other, you're not making chemical bonds within each of those layers. If you were, you'd then have it. You'd have a nice little conductive situation, but it doesn't work that way. But if you were to take your lead pencil, well, it's not lead, graphite pencil, take the lead out or expose it on both ends, touch that to a conductivity meter, you do get conductivity because it's one big crystal that you've got there and you're laying off layers as it comes along. All right, so we write with it. Another important property that it's very slippery. I grew up on a farm, so applications that I saw graphite for, my father would, or instruct me or whatever, in a corn planter or a grain planter, all the moving parts, you don't want to put grease in there because grease is sticky, and any seeds that would get caught up in the grease wouldn't be able to, go into the ground because they would be stuck and gummed up in the grease. So in the grain, you would just dump in some graphite powder. And so as the graphite went through the machinery with the seeds, the machinery would get a coating of graphite, and graphite is very slippery because each of those layers come off so easily. You then have this coating of graphite on all of the working parts, and that provides lubrication, right? You can actually get graphite paint. My father went and purchased some graphite paint and painted the interior of all of the wagons or gravity boxes so that the grain would come out smoother. And then he would fail to tell us when he said, go climb up in there and empty that wagon out. I remember the first time I climbed in, took a step on the bottom, bang, bang, on the bottom of the wagon because you slip and slide out. He said, oh, watch that, I painted that with some graphite paint. Thanks, that's good, it was good information. Thanks for telling. So graphite is very slippery. Okay, just to go off on a side, and I wanted to add some pictures to your little handout, but actually I will show them to you online. Since we do have a little bit of time, I'm going to just show you something here. So if I do a little search here for carbon, let's go with nanotubes, carbon nanotubes. This is something, again, that is, let's go with images. All right. Now, you may have seen pictures like this on Sheldon's T-shirt if you've watched The Big Bang Theory, right? He wears this T-shirt that says carbon nanotubes. Now, these are actual structures. There are, in the last, I would say, 7 or 8 years, chemists have been able to take graphite and carefully remove one layer of the graphite, all right? So you take that stuff and you take one layer off. When you take one layer off, you have a slightly different compound because it's not interacting with the other layers. And they've called a single layer of graphite, they've called that graphene, all right? Just a different name. And they've measured how strong this graphene is by putting forces on it. And in terms of strength per mass, graphene is turning out to be the strongest material, even stronger than diamond. It's able to withhold more force per mass than diamond structure, all right? So graphene is conductive, and it's super thin. It's essentially a sheet of carbon atoms. And scientists and technologists envision making electronic devices by one layer of carbon atoms, super small electronic devices. Not only can they create single layers, and the way they created it, you can create a graphene layer, and I've tried it, and I don't know whether it works or not, but you can create a graphene layer, they say, by laying down some pencil and using tape, clear tape, and you should be able to get a graphene layer from that. I have not been able to test it. So I put it down, I take a layer off, I'm like, oh, have I made some? I don't know what I'm doing here. Other things that can be formed. You can see it in this image here. I don't know if it'll be larger if I click on it. Right here, this D, this is what is called a buckyball. This was determined in the 60s. Various ways of, when you heat graphite and do various things with it, you can get single layers to fracture and then roll up on each other and make a sphere of sp2 hybridized. They're kind of being bent, but you can make essentially a soccer ball shape, all right? Chemists are now able to then take a nanotube, which is essentially a graphene layer that's been wrapped around into a little tube, and you can then take the end of a buckyball, put it on the end, and you can make a little nano capsule. Some biologists envision putting single molecules of various medicine, right? You know what I mean, medicine, and actually use them to inject individual cells with individual molecules, somehow using them to get the medicine within there. Last couple of years, I've heard these nanotubes being applied to, say, mice, various things, are initiating cancerous tumors. So, you know, it's dangerous. Not sure whether that's what to do, but this is what's really happening on the edge of surface science, all right? So that's kind of neat stuff, too. All right. Delocalized pi structure that extends, it conducts. I'm going to put one last bit of information with this, because it is a neat thing. A single layer is called graphene. All right? Just to kind of keep it up to date with what we're seeing today. All right, one last example of this, and I'm not going to write a lot about it. I just wanted you to show it to you. And this one is our silicon dioxide. And the only reason I've got this in here is because, right, carbon dioxide, CO2, obviously a gas. It's interesting, carbon dioxide, for some reason, does not form a covalent network crystal. You think it could because it's very much related to silicon dioxide. But in silicon dioxide, and we'll take a look at this guy, right, there we've got our Si. And you can see here, it's not like a carbon dioxide. It's definitely not carbon double bonded with another carbon. It's definitely not that structure. But what it is, that guy is covalently bonded to 4 oxygens, and then that oxygen bond is opened up, and it's covalently bonded to another sulfur, which is then covalently bonded to 4 oxygens. So again, it is a covalent network crystal. You might see SiO2, you might want to draw it like carbon dioxide, but in actual fact, it is not. I guess I could add here, right, covalent bond to 4 oxygens for that silicon. And this is quartz. All right, this is a quartz crystal. All right, this is quartz. Glass, also silicon dioxide, but it's a disorganized version of it. That's the difference between a crystal and a glass. Glass is actually a representation of a state of matter. It doesn't have to be glass, the way we envision it. Glass is essentially a crystal that didn't quite get itself organized enough. So it's got various degrees of organization within the bulk of the glass, but there's not complete connections from one end to the other, which means glass can flow. Those non-connections are able to flow past each other. You heat up glass and it flows readily. But even the glass that's right here in this window is currently flowing. Because its temperature is high enough, because its temperature isn't high enough to flow like you see when they're blowing glass, it's flowing incredibly slow. All right? They've taken glass from like 100-year-old houses, and when you take that glass, you can measure a thickness difference in the bottom of the glass than the top, which wasn't there when they installed the glass. Gravity essentially is pulling the glass down. It's slow, it's flowing, but it's incredibly slow that it's flowing. So glass is actually a liquid because it hasn't made enough connections to make it a covalent network crystal. Okay? So that's kind of neat. They're now talking about making various types of metallic glass, which means it's a metallic crystal that has somehow broken those connections between the whole crystal, and it's able then to have these special properties. It may not be transparent metallic glass, but it's the connectivity and the fact that it flows very slowly that makes it a glass. All right, so there's a little side information as well. No, that's not what I want to do. I want to simply get to the end. Okay, so some properties of this stuff. These are just bulk properties instead of some of the specific ones. But I do feel it's important that we talk a little bit about diamond and graphite, some very important covalent network crystals. Yep. Okay. The review questions are at the end of this note and all that other good stuff. It should be online, and I'm going to put this movie up online anyway, so you can track that. They can break. You can shatter a crystal. You just need to put enough force on it. You can shave off pieces of crystals. That's what diamond cutters do. They know exactly where those 3D or where those sp3 bonds are, and they'll take a grindstone and they'll essentially not melt away, but burn off some of the carbon, make a nice shaped diamond. Very high melting point, boiling points. They really don't melt. We say we give them a melting point, but they really don't. I guess graphite, because it's got that weak interaction between each layer, could somehow have the layer start to peel off before each layer starts to fall to pieces. Essentially, if you're melting or boiling it, you're chemically reacting it. You're breaking the intramolecular, not intramolecular forces. You're breaking the bonds. It's undergoing a chemical change. So if you were to take a quartz crystal and get it hot enough and melt it, it may appear to melt, but when you cool it back down, you end up with glass instead of a nice quartz crystal, because it never gets itself organized again the way it was. You melt a diamond, you're not going to get a diamond back. It's gone. It's been turned into something else. Sorry, insoluble. I don't know why I have all these animations. Water cannot break the bonds. It just holds together. Oh, excellent. Non-conductors. Excellent. I love animations. I don't even know why they're there. Gotta get rid of them.
much stronger. Hold on one second. Due to the 3D arrangement of crystals, overall structure much stronger. Covalent bonds that it makes up. It's very strong. We know this. It's very stronger than, much stronger than ionic. Do I want all this information? No, I don't think so. I think we get the idea.
This came out of the old textbook. It's not a big deal. It kind of ranks what we've talked about. All right, ionic compounds, hard, brittle, high melting point. All right, liquids conduct. Again, all of these things here, the conductivity and the melting point, you're looking at the directionality of the bonds, right? And you're looking at the whether it's a localized electrons or not. Metallic is a special case, even though the bonds are not directional. It has high melting points because the bond is so big, it's able to accommodate that vibration. So that's a special case on that. So I don't think this is worth writing down. These are just the type of questions that you're going to be asked. So it's just giving you a heads up. What bonds or intermolecular forces must be broken upon vaporization? Even though we really can't vaporize diamond, we can, well, I guess we could vaporize it, but you'd never get it back. It would never condense back into diamond. What kind of bonds are we breaking when diamond undergoes this type of a change? Yep. Yeah, it's a covalent bond. It's not like an intermolecular bond or an H bond. It's a covalent bond. We're breaking the molecule itself. Covalent. So if we have something like solid CO2 and we melt it, well, actually it sublimes. It becomes a gas. What kind of bonds are holding the CO2 molecules together in that solid that we must break in order to initiate vaporization? Now here's the logic. Covalent network crystals, covalent. This is a small molecule, right? Small molecule molecular solid, which means you're thinking intermolecular forces. What intermolecular force holds that molecule together? Holds adjacent molecules together. What intermolecular force holds those things together? This is the Monday morning pause. Here we go. Yep. Dipole forces. What does CO2 look like? Looks like this. Beautiful. It's not dipole forces. Because that's the actual shape. It's linear. Which means it looks like this. So what forces hold adjacent carbon dioxide molecules together in the solid? Yep. Yeah, London forces. It's non-polar. Non-polar molecule, therefore London. We'll get the hang of it. We're getting there. SiO2. What bonds are being broken when you heat the heck out of that thing? I think Kirsten has it. What do we got? Yeah, it's covalent. It's a covalent network crystal, so we've got to break the covalent bond. Al, aluminum. What kind of bonds are being broken there when we melt aluminum? Is it ionic? No. Is it a small molecule? No. What is it? It's what's that? It's a metallic crystal. So we're going to break a metallic bond, and that's what we call that big delocalized electron C bond. It's simply called a metallic bond. So we're breaking metallic bonds. All right? Okay? Sodium fluoride. What kind of bonds are being broken there? Yep. Ionic bonds. Full opposite charges. We're breaking ionic bonds. SiC. What are we breaking there? Yep. Why would you say covalent? They're both nonmetals? All right. This is one of those covalent network crystals that is in the list that I need you to memorize. So this is not a regular small molecule. This forms a covalent network crystal. If you take a look at your little list on covalent network crystals. So therefore, it's just like diamond, silicon dioxide, silicon carbide. It's just covalent bonds because it is a repeating structure of covalent bonds. Covalent. Because it is a network crystal as well. All right, so you can't treat it like a small molecule. NH3, what is being broken there? So it's a small molecule. Now we got to think what intermolecular forces are at play to hold that thing together. What do you think? Yeah, that's an H bonding. H bonds. All right? Ionic is ionic, if it's an ionic compound. If it is a metal, metallic bonding, we're breaking. If it is a covalent network crystal, one of those I asked you to memorize, covalent bonds are being broken. And if it's a small molecule, molecular crystal, then you have to default back to what we did in the previous lessons to figure out whether it is polar or non-polar, et cetera, et cetera. I didn't have a simple dipole in there. I could add what would be a simple dipole, HCl. All right? It's not a hydrogen bonded to a carbon, not hydrogen bonded to an oxygen, nitrogen, or fluorine. So HCl would be dipole. Dip. Okay? Again, I don't think it's worth writing down, but again, it's all online. You can go back and look at it. Which would have the higher melting point? SiO2 or CO2? Yes, Jess? SiO2. SiO2. Why is that? What is silicon dioxide? Yes, but just let's use, why is that, right? And what are you chemically breaking? Yeah, it's a covalent network solid, and if we just want the higher melting point, just tell me it's a covalent network solid, and it's got very directional, strong covalent bonds holding the crystal together, right? Covalent network solid with strong covalent directional bonds, right? CO2 is a small molecule molecular crystal with London forces holding them together. Not even a chance. Al or CH4? Yep. Has a higher melting point? Nope. Aluminum. Aluminum is a metallic. Metallic crystal. And I can't spell crystal this morning. Metallic crystal. Oh man, I'm losing it. Right, again, it's got a strong electron C holding those electrons together. CH4, what's holding CH4 molecules together? London forces, very weak, all right? Metallic crystal is a strong, oh goodness, strong, I don't even know how we want to describe this, strong electron C, holding it together. NaCl or NH3? Which one do you want? Yep. NaCl, I agree. Why NaCl? it's ionic versus H bonding, and the complete charge is going to be stronger than the dipoles in the H bonding, right? It's ionic, and therefore strong directional forces holding it together. Okay? All right. So there's some homework associated with that, along with your review. Again, with the new textbook, I've kind of I did a quick little look at the questions. You'll notice I've left a few of them out, things that I didn't necessarily discuss, but you might come across that in some of those other questions at the end. And if that's the case, we'll discuss it tomorrow.